Okay, let's do WFA number 11. Let's see what the problems are. Okay, so a uniform disc, thin hoop, uniform... Okay, so a disc, thin hoop, and uniform sphere, all with the same mass, and same outer radius, each free to rotate about a fixed axis. And then the hoop is connected to the axis by very light spokes. Okay, so, this is this is just T net equals I alpha problem, right? Because really they each have the same torques being applied, since the force is being applied, it's being applied like at the rims, so same radius, and then it's being applied at the same, by the same force, right? So R cross F equals I alpha, or at least the magnitude of R cross F equals I alpha. And so if they each have the same torque, I know the greatest rotational inertias will result in the smallest angular accelerations. So I know the disc will have the least, and then the hoop, and then the sphere. Right? I know this by memorizing the equations, but also I know a disc for sure will have all the mass concentrated on the outside. A disc will have some of that mass distributed on the inside, and then a sphere is kind of like pushing the ends of the disc towards the axis of rotation. So we have like this disc radius, and this is, I think, okay, this is all horizontal, I guess. And we have a force. So it's like this sort of horizontal pulley thing, which is really interesting. And oh my god, this is gonna be kind of a rough derivation. We're gonna have to kind of do some derivation here. So I know T net. So this is a two-body problem, right? So we're gonna have this tension on the block T, and then we're gonna have this force F. So we know that by Newton's second law, the tension T is going to equal ma, and we know the torque on this disc is going to equal F. So the T net is going to equal I alpha. So I know that we're going to have the torque net is going to be force times R1 minus tension times R2, which is going to equal the rotational inertia times so this is kind of, so I guess the whole thing rotates like together. That's my guess. Yeah, so it's free to rotate. Okay, so then we can use A over R2 because it's going to rotate the whole thing instead of just the middle disc or whatever. So force times R1. Now the tension is going to equal ma, so I'm going to have ma times R2 is going to equal I times alpha over R2. So I'm going to have all my A terms, so F times R1 is going to equal I alpha over R2 plus ma R2. And I can do some fraction manipulation. I can multiply everything on the top by R2, like so. So what I did is I just did R2 times R2. Or no. Yeah, okay, so this should be squared, I think. And then I can multiply by R2. I could factor out, and this should be A, whoopsies. Factor out the A, and I'm going to be dividing by I plus mr squared. Kind of a rough derivation, but it's all good. Object rotates so that its angular acceleration is proportional to t to the negative 3/4. Okay, that's really annoying. So what that means is, oh my goodness. So that means that its angular acceleration is proportional to 1 over t to the 4th. 3/4. So as the angular acceleration increases, or as time increases, the angular acceleration goes down. And when t is like really close to 0, it's like a really high angular acceleration. So I'm going to guess it's graph D. Idea being that after a long period of time, the kinetic energy essentially flatlines. So, when t approaches infinity, right, alpha is going to be 0. So that means omega is going to be constant. They simultaneously start from rest at the top of an inclined plane. So this is I'm pretty confident this one's going to be that they arrive together, right? If you have two cylinders. Reason being, you can do the math and you can show that, it's this weird thing that I still need to kind of wrap my head around, is that when you have, we know when you have like a certain frictional force, that's going to create a certain torque that's proportional by r. So when you increase the torque, you would expect to get double the angular acceleration, right? But your rotational inertia scales by r squared. So if you have twice the torque, you also get 4 times the rotational inertia. So you get half the angular acceleration. But we know A is equal to alpha times r. So if you have half the acceleration but then double the radius, you get the same linear acceleration. So everything kind of scales out. And everything scales out so that it's only this fraction that's really making a difference, right? And obviously we know mass won't really make a difference because you have twice the mg, you have twice the, so on and so forth. You have twice the mass, twice the inertia, but then also twice the force gravity. So everything kind of balances out pretty nice. All 3 objects shown have the same total mass and also the same vertical span. All right. So we have something like this. Okay, this is pretty interesting. This is a pretty interesting problem. So I'm pretty sure 1 and 3 should have the most, and reason being is I could smear these two these like 2 point masses out into a circle, but because they still remain the same distance from the rotational inertia, or from the axis of rotation, they have the same rotational inertia, right? I'm not bringing the mass closer to the center, but I think in the case of a square, if these are the same two distances, then some of this mass is getting closer. Like if this is a distance r, this would be r over root 2 right there. Or I guess I should probably draw it here. If this is r being the radius of the circle, which is also half the diagonal length, this would be r over root 2 if you do some geometry. So I think 1 and 3 are going to be our winner here. This is a classic torque problem. We want to find the magnitude of the tension in the string BD, BD. So we want to put our axis of rotation at over here by CA. So we're going to have 96 newtons here. We're going to have 60 newtons here. And we're going to have, the tension here. So these two forces are going to create torques in the same direction. This is going to create a torque in the opposite direction. So, that's bad. So I can say that's going to refresh for me. The torque net is good. I'm just going to kind of skip some steps because we're kind of crunching. Oh, I guess I have time, but I think hopefully you're familiar with just doing a torque net, or I should use tau. Torque left is going to equal torque right, or not. I don't know why I say left right. It's really counterclockwise and clockwise. But regardless, so we know the tension times L is going to equal the force by P times R1 plus the weight times R2, and I can just plug in distances, right? So T is going to equal, L is I think 1.2 meters. Oh my goodness. 96 times 0.3 plus the weight times, so the weight is 16, times 0.6, which is half the distance, and I'm just dividing to solve. to solve for t. So if I just do that real quick, 96 times 0.3 plus 16 times 0.6 divide by 0.3, or no, 1.2, what am I doing? Times 0.3 by 1.2, I get 32 newtons. So let's see how I did. Oh, I missed one. Okay, so let's see. Oh, this is really silly. Yeah, the hoop for sure should have the least angular acceleration because all the mass is distributed on the outside. Everything else looks nice. All right, thank you for